I'm Matney with the Cooperative Extension Service in the Kenai District, and I work for the University of Alaska Fairbanks. Tonight we're going to be talking about soil testing and interpreting a soil test. Those of you that may have not done it before, there's going to be a lot that we'll cover. If you have done it before, hopefully we refine everything you already know and you learn a little bit more. So when you look at a soil test and you get it back from the lab, it's not always easy to interpret on your own. What most people notice is that it leaves you wondering what your crop actually needs in determining what the numbers say on the paper. And then also, how do you know how much fertilizer to add in relation to what it says on the paper? So tonight we're going to be going over these things, and hopefully you guys will feel a lot more comfortable with it. So the questions you might have when you get your soil test back are, can you tell me what this means? How did they come up with these numbers? Do I have good soil? And what should I do to make my soil better? Whether you're gardening or farming, there's going to be a lot of those things on your mind. Our goal for today is to take you from maybe a mild state of not understanding what the soil report says to completely understanding the report and just knowing what the basics are. So before we get into the soil tests, we're going to do a quick refresher on what soil sampling is and how to do it. So how do we take a soil sample? And this example is for any vegetable, small fruit, regular home garden, any of your fields or pastures that you might be working with. You're going to use either a shovel or a trowel. And if you think about this little rectangle on the left, you're going to be picturing some kind of square or rectangle, and then you're going to pick points spread across that. It doesn't have to be exactly random. You just need it to be representative of the whole area that you're looking at. Then once you've got those samples, you're going to do something with them. And what we're going to do is we're going to mix that into a bucket, and we're going to make sure that we've got enough in there that's representative again. So if we've got 13 points across our area, we're going to mix it all in a pail, spin it around, and then we're going to take at least 2 cups of soil back out of that bucket and then put it in a bag so that we can send it to a lab. If the soil is super wet, we're going to put it on some newspaper so it can sit there overnight. That will help things out a little bit, and because you don't want things to be too wet. And then also, when you're thinking about where you're going to send things off to, you need to know what lab you're going to send it to. We do have a fact sheet that talks about the different labs that you could choose to send your soil sample to. But again, it's just 2 cups of soil that you would send to the lab. Looking at the plant roots here, the soils have ions in them with nutrients, and as the water moves across the root interface, it can carry nutrients to the root. And so one way is through mass flow. As the water moves across the root, it carries it to the root. The other is the way where there's already some water in the soil. It's not really moving with gravity or anything like that. And the soil ions are diffusing towards the root where there's an area of low concentration. And then the other thing that the way that the plant receives nutrients is also when it grows. And so this little image at the bottom here where it says root interception, that's where the root is moving down through the soil, and each time it moves to a new area as it grows, it's encountering new nutrients. And so that's the other way the plants uptake nutrients. Okay, so let's go back to the soil tests. So when you send your sample off to the lab, this is an example of a report that you would get back. You can see here with these yellow arrows that there are 5 different spots across the soil area. Each one of those indicates a different soil range. Every one will be just a little bit different. Okay, so when you get back your soil report, first you're going to look at is to make sure it's got your proper name and your proper location on there. If it doesn't, that means you've probably got somebody else's. Looking at your sample location, that's where it's located. Going down and looking at the samples you sent in, those also need to be clearly labeled. If they are not, then you won't know what it's relating to. So if you're sending in more than one sample, it's important that you remember and mark where they came from. Okay, so let's talk about what actually is in the soil report. The most important thing is pH. Of all the things you're going to look at, pH influences almost everything else. So let's take a look at pH. So pH, what is it? Is actually a measure of the potential for hydrogen. As there's more hydrogen in the soil, it affects your soil and actually makes it more acidic. As there's less hydrogen, it actually goes towards alkaline. There's two measurements your lab will look at. There's the actual pH, where they just take your soil and mix it with a little bit of water and take the measurement. And then there's the buffer pH. The buffer pH is actually an indicator from adding a reagent to the soil and then measuring how much it's changed after that addition has been added. So it's an index for lime. So it's simulating putting lime in the soil and seeing how far the soil pH changes. This buffer pH is great for us because it tells us how much lime we need to add to the soil in order to increase our soil pH. In Alaska, usually our soils are acidic and we need to increase the soil pH. So what do most vegetables prefer in terms of pH? I was going to make this a question for you guys, but the answer is somewhere between 6 and 7. The ideal pH is right around 6.5, and we're going to talk about why that is in just a second. So if we look at the pH range and then the different types of nutrients that are potentially available in the soil, that range of 6 to 7 here is denoted in yellow. And it being in yellow shows a wide range of just 6 to 7, which is 1 point of pH. All of those other lines that are running horizontal across this graph show the relative amount of that type of nutrient in the soil as it changes with pH. As you can see, if you go to the left and get more acidic, a lot of those things actually become less available. Specifically, all the important things the plant needs, like nitrogen, phosphorus, potassium, sulfur, calcium, and magnesium. If you go the other direction, it actually doesn't start to really get limiting until you get close to about 8 for most of those nutrients. So in general, 6 to 7 is a good pH for us because as our soils are fairly acidic, raising that soil pH to that minimum range is good. And then there's a little blue band here in that range that shows us that if we can ideally get the pH right around 6.5, it's going to maximize most of those nutrients for our plants. And so that's really where we're going to be trying to target, is that 6.5 zone. Here is an index for you to determine how much lime you would need to add to soil to change the pH. So on the left, we've got that buffer score. And remember, that's an indicator of how much lime we would need to add. Well, when we look this up on our chart, if we've got a buffer score of 5.7, we're going to need to add about 4.6 tons per acre to change our lime to 6.5. That's a lot of lime, and if you're just working on a 100 square foot level, that would be about 21 pounds of lime per 100 square feet. So for a 10 foot by 10 foot area, you need 21 pounds of lime. At the top there on the green line, you can see that the buffer score being at 6.4 for pH, you would actually need a lot less lime at 1.9 tons per acre or only 9 pounds per 100 square feet. So having that buffer score is really crucial to being able to adjust the lime amount that you add to your soil. And of course, when you have proper pH, it means the nutrients are more available to plants, and it makes the soil environment more suitable for diverse microbial activity. Because if it's too acidic, you're not going to have a good variety of microbes in the soil. And if it's really high in alkalinity, it's going to be exactly the same. So what else should we know besides pH? There's lots of other things, and so pH is the most important one. So let's go to the next one, cation exchange capacity. The best way to think about cation exchange capacity is think about it as the total number of parking spots your soil has within it to hold nutrients. A lot of the soil particles in a soil, if it's a mineral soil, doesn't have much organics in it, it's not going to have a lot of parking spots. It's not going to have a lot of good surface area to hold nutrients. If we've got a really rich soil with lots of organic matter in it, it's actually going to have a very high level of cation exchange capacity, especially if it has a fair amount of silt or clay in it. It's going to have a lot of cation exchange capacity, so it's going to have a lot of parking spots. So when we think about parking spots in the relative number we're looking for, okay, less than 10 usually indicates that you've got kind of a sandy soil. 10 to 20 means you usually got some kind of a mixed texture soil, maybe like a silty sand. And then once you get over a score of 20, It usually means you have a high level of organic matter or you've got a fine textured soil, like mostly clay. Here in Alaska, we don't have a lot of high clay soils. Most of our soils are not super well developed, which means they haven't sat in place and weathered in place because we've had a lot of glacial movement, we've had a lot of volcanic activity. And so there's some differences between Alaska and the lower 48, but there is some clay in Alaska. The other main thing to look at here is that the cation exchange capacity is an index of the number of positively charged cations that the soil can hold. So those are the things that are the parking spots in the soil that need to be filled. Organic matter. Organic matter is very important in soil. It gives its ability to hold water and nutrients. The way the soil lab actually measures organic matter is they heat up that soil sample you sent them to 360 degrees Celsius. And the amount of weight that is lost after that heating is a determinant of the percentage of organic matter present in that soil. A lot of the organic matter that you encounter in Alaska is probably either going to be a mix of kind of like peat in the soil, or it could be a little bit of a woody debris that's broken down from previous forests and things like that. We do have areas that are fairly high organic matter, but it's not usually holding a lot of nutrients. Okay, so when we think about the amount of nutrients in the soil, organic matter is not always an indicator of there being lots of nutrients. Organic matter is very important in determining not only how much nutrients and water soil holds, but it also helps us interpret it how we measure all the nutrients that are in it. So if we have a soil that's above 19 to 20% organic matter, that's actually what we consider an organic soil. So it completely changes the way we think about lime and how much lime needs to be added. If we have a mineral soil that's below 19% organic matter, it's a lot more linear in terms of the soil response to lime and other nutrients. That's because the organic matter itself actually acts as a buffer in the system. When you've got lots of organic matter, it holds water, it holds nutrients, it gives it up, it takes it, holds it fairly easily. And the other main thing to know about high organic matter soils is that the ideal pH, instead of being right around just 6.5, it actually moves down the acidic scale to about 5.8 to 6.5. So that means if you've got high organic matter above 20%, you don't need to lime your soil all the way up to 6.5. Once you get above about 5.8, you're doing okay. So this is what your ideal pH might look like if you have a high organic soil. Again, it's just that range from about 5.8 to 6.5, and that's what that yellow band here represents. So estimated nitrogen release. Many of you guys will notice that there is an estimated nitrogen release. And because of that, what we usually do is just disregard that for most of the places here in Alaska. Because our climate is fairly cold, actually the soil sits near freezing for some places from right around October all the way into May. And because of that, that nitrogen actually isn't getting broken down from the organic matter not breaking down. So when we look at organic matter and come up with an estimate for estimated nitrogen release from that decaying over time, it just doesn't happen very quickly in Alaska. It does happen in the summer, but our soils are usually somewhere at 60 degrees or a little bit less. So there's not a lot happening very quickly. So we kind of disregard that in terms of thinking about normal fertilizer recommendations. So a lot of the soil samples you'll get back will be super high, but that doesn't necessarily help us too much. The other thing that we look at when the soil sample comes back is all of the MELIC3 extractables. MELIC3 is actually the method that they use to determine most of the things we need to know in the soil sample. Things like potassium, calcium, sodium, magnesium, iron, manganese, copper, zinc, boron, sulfur, and phosphorus. It's just the method we use. There are other methods like the Bray method, and all of those other methods do not work as well for Alaska because of the organic matter we have, the acidity we have, and then also the parent materials we have from a lot of our soils being volcanic in origin, a lot of silt, a lot of sand. The MELIC3 method is actually the truest to true numbers that we can find. So using the MELIC3 method in the lab, We can look at our soil report here, and we can see that we've got sulfur listed up at the top. Right below that, we've got phosphorus, and then we've got calcium and magnesium and potassium and sodium. And then because we know those numbers, it also tells us what the base saturation can be in relation to the cation exchange capacity. If this seems like I'm going over your head, don't worry, we're going to actually go over that whole area here in just a moment. And then when we start looking at some of the other minor nutrients that are available in the soil, boron, iron, manganese, copper, zinc, aluminum, and then of course one of the macronutrients, very important ones, is nitrogen. And so those are some of the things we're looking at, and a lot of those numbers come from the MELEC 3 method. So let's talk about the big three nutrients. These are the ones that everyone needs to know: nitrogen, phosphorus, potassium. What we need to know is that the phosphorus is up here at the top, and we're looking at parts per million. Most of the recommendations I make are in terms of this part per million. This sample has a level of 22. The ideal range for phosphorus is actually between 100 to 170 parts per million. So this tells us right here that we're going to want to add phosphorus. And in fact, each year you want to actually add a little bit of phosphorus to your soil. It's one of those things where you're going to need a little annual adjustment each year, even if you have relatively high numbers, just because you can't always count on our phosphorus being available in Alaska soils. For our potassium, this is where we find it on the soil report. Right here it's listed as 28 parts per million. The ideal range is actually 150 to 220 parts per million. Anywhere in that range will actually give you a fair amount of productivity. So that's the number we're looking for there. When we think of in terms of nitrogen, there's actually two numbers that are measured. There's the nitrate nitrogen, is the NO3N, and then we have the ammonium nitrogen, which is the NH4N. The nitrate nitrogen we like to have between 25 to 75 parts per million. If you have plants like lettuce that need a little bit more nitrogen, you might need them to be up towards the 75 parts per million. If you have other things like root crops that you don't want to have big tops, but you want them to have nice big roots, we will probably cut back on the nitrogen a little bit. And of course, going into that total nitrogen calculation is ammonium nitrogen. And we want that to be below 10 parts per million. The key reason for that being is that the ammonium nitrogen is a little bit different for availability of the plants, and this is the number we start to see climb when people add lots of conventional fertilizers. If they add a little bit too much, a lot of it's just sitting there as ammonium nitrogen. Other important nutrients we need to look at on the chart are sulfur, calcium, magnesium. We're going to go across these right now. So looking at sulfur, here it's rated as 18. Ideally, we'd want it between 15 to 25. So this number is actually okay for us. The other number that we're looking at here down below is calcium. Most of our soils actually have a fair bit of calcium, so I don't usually see that as a deficiency. Anywhere above 250 parts per million is a bare minimum. We see this go all the way up to 1,000, no problem, here in our soils in Alaska. Magnesium, here we have 50 parts per million. Ideally, we want above 150 parts per million. That helps create the proper range between calcium and magnesium. If you don't have one of these in the right balance, one of them will be a little bit more available to plants than the other. So we need to make sure that in this case we would raise magnesium. Sodium is something you do not want to have in your soil. You don't want to have sodium. So usually we want to have below 100 parts per million. Instances where you start to see sodium climb is when you use a lot of kelp or marine environment types of fertilizers in your soil, or if you've had a high tunnel and you've used limited irrigation and you haven't had the top off your high tunnel for a while. What happens is as things evaporate and as the plants transpirate, they're pulling water up from deeper depths. So over time, that sodium starts to build up towards the surface. So that's something that you want to manage later on if that occurs. But again, we're looking for below 100 parts per million for sodium. For boron, we don't need very much at all. We only need 1 to 2 parts per million. So here it being 0.2 is actually extremely low. A lot of soil samples that you will see from Alaska where it has not been farmed or amended with any fertilizer is it will be below 0.5. And 0.5 is considered kind of the bare minimum needed for most vegetable growth. So we want to raise that up to somewhere between 1 to 2 parts per million. Looking at some more micronutrients, things are like copper and manganese. We go down here. Iron is included here. Most of our soils are not deficient in iron at all, and you just need above 5 parts per million for iron. Manganese, you need above 2 parts per million. Copper, we want between 1 and 2 parts per million, and zinc the same. We want somewhere between 1 and 2 parts per million. Now, often you might see copper be a little bit higher and zinc be a little bit higher, and that's fine. Nothing to worry about. And aluminum here in Alaska, usually see the numbers being fairly high. That's not an issue, and it really only becomes an issue when your pH gets below 5, but most of us don't have to worry about that anyway because our soils are usually going to be somewhere around 6. So again, aluminum's not too much to worry about for us. Base saturation. So let's go back and look at those percentages of nutrients relative to the cation exchange capacity. That cation exchange capacity, again, is just how many parking spots you have in your soil. And when we think about the percentage of cations in the soil, which is this base saturation, we're really just taking the total number of parking spots and dividing that among calcium and magnesium, potassium, sodium, other bases, and hydrogen. So it's breaking that 100% down into this level. So if we assume that about 100% is all these numbers added together, it's just breaking it down in percentages here. So about 41% of our cation exchange capacity is calcium, almost 9% is magnesium, about 1.5% is potassium, 2.6% is sodium, 7% is a mix of other types of bases of cations, and then hydrogen actually takes up 39%. This means and tells me that our pH is actually quite low. As your pH is more acidic, hydrogen levels are much higher. So we don't want that to be the case for us. So we want to try and get our hydrogen level at 10% or less, which means that we're going to have at least 90% of our soil holding nutrients or cations that our plants like to use for fertilizer. If it's 39% hydrogen, you only have about 61% of that soil space available for nutrients for fertilizer. So that hydrogen tells you how much room is already being taken up and not used in your soil. So the way we raise that is by adding lime, and that raises the pH, and then that makes calcium and magnesium, potassium, sodium all have more places to park, and it can hold more nutrients. If we look here at our calcium levels, the ideal range when we look at relative amounts, 60 to 80% for base saturation is where we want to be for calcium. For magnesium, we want to be somewhere between 10 and 20%, especially when it gets below 10%. We definitely probably want to think about fertilizing. But before we do anything, you can see here I listed always fix your pH first, because if we raise our pH and get rid of almost all of our hydrogen numbers here, all of these other numbers will increase proportionally. So if we get rid of that 39% hydrogen, all of the calcium, all of the magnesium, and all of the potassium will bump up in terms of numbers. Again, potassium levels near 3% to 8% are a good target. They can vary a little bit more widely than that, but you definitely want them above probably about 3%. If you get in that 5 to 8% range, you're doing okay. And then ideally, we want to keep our sodium levels low. So you can see here our sodium levels are already at 2.6%. We'd like to try and drop those if possible. Really, the only way that we're going to be able to do that is to limit the amount of manure, limit the amount of conventional fertilizers that are high in salt to our soil, and then also we might want to do some flush irrigation. If we add 3 to 4 inches of water in a one-time event, slowly over time, so like over a day or two to our soil, it actually will wash out some of those salts, that sodium, and take it to deeper depths in the soil and remove it from the rooting area of our plants. That's really our main tool we have to reduce sodium. Soluble salts. These are also something we worry about in high tunnels. And these consist usually of sodium and calcium and magnesium. although others can be present. So what is soluble salts? Actually, it's a measure of electrical conductivity, and the number we want to see on here is something below 0.6. It actually can get higher than that, and your soil can do okay, but when we know we need to start managing our soluble salts and trying to reduce them, it's right when we start to get to 0.6. So that's something to keep in mind. In the same way we manage soluble salts is the same way we manage sodium, is to apply water and try and wash some of those salts out and reduce the amount of high salt fertilizers and manure we add to our soil. Okay, looking at your relative salt index for several different types of fertilizers, I've got them listed here. And again, I'm going to make this presentation and recording available later. So we've got sodium nitrate, potassium chloride, and ammonium nitrate as kind of the big three that hold a lot of salt. As you go down in scale here through the middle, there's a lot of common fertilizers people use in there. And then as you get towards the bottom, things that actually don't have a lot of salt are the phosphorus fertilizers like diammonium phosphate, concentrated superphosphate, and gypsum. So again, most of the time you're seeing here is when we've got some nitrogen fertilizers and those with chloride in them. So when we think about soluble salts and the electrical conductivity that they contain, what kind of plants will be affected and what level will they be affected? Whenever we see electrical conductivity between 0 and 2, most of our plants can handle that. But again, like I said, once you get to about 0.6, you want to really start managing it. When you get to between 2.1 and 4 on the electrical conductivity scale for EC, that's considered slightly saline, and some of the plants like strawberries and things like that can start to be affected. 4 to 8, you're starting to get pretty darn saline, and then once you get above 8, you're starting to be strongly saline. So let's take a look at a chart here that tells you how different plants are affected. So on this chart here, those plants that really cannot handle soluble salts increasing, okay, are things to be things like blueberry, carrot, green beans, onions and peas and radish. Raspberries don't like it either. Then also strawberries don't like it. Some of those other species listed in there are other common garden plants. Those that are slightly tolerant of soluble salts include apples, cabbage and celery, cucumbers and grapes, lettuce, potatoes, and then also sweet corn. When we start getting much higher in salinity, those that are moderately tolerant include beet, broccoli, spinach, squash, and tomato. And then when you have very saline soils, you're really just kind of left with Swiss chard and asparagus. So you can see as you start to increase your salinity, you're going to be able to grow less and less things, and they're not going to do so well. So if you can keep it low, you can grow a wider variety of plants. So phosphorus, how much is enough? Let's take a look at this in detail. This is one of the main things that are a concern in Alaska. Our soils are very deficient in phosphorus. So we can see here in this example report, this one had a phosphorus level of 22 parts per million. The Extension Service has put these to work into easy to use charts. And so for some of our soils, if we're thinking about phosphorus and you happen to have this soil series here listed, and these are some very common soil series we have on the Kenai Peninsula. If you have a soil phosphorus level below 35 parts per million, you're going to need about 150 pounds per acre, which is a lot of phosphorus. If you have different levels, it's going to change the amount of levels you need. And my soil calculator, which I will show you guys in a little bit, actually calculates all of this for you. Looking at nitrogen levels, how much is enough? Our nitrogen actually gets lost every year. One of the ways is due to leaching. So when it rains and washes away your nitrogen, it's pulling your nitrogen away from your soil. Voltization, which means it's actually being heated up and moved away through the air. If you guys know this, the atmosphere is actually full of a lot of nitrogen, and it's mostly nitrogen. And denitrification actually includes the breakdown of nitrogen in soils, usually when it's warm and wet. Other ways we lose nitrogen is through microbial processes. So a lot of the bacteria that are in the soil actually consume nitrogen as they break things down. And so we'll lose some nitrogen that way as well. In terms of how much nitrogen you need to apply each year for a lot of our high nitrogen needing plants that we have in our vegetable gardens, you can see the highest ones include the big plants, the broccoli, the cabbage, cauliflower and celery, and also lettuce. Anything that's producing a lot of biomass above ground is going to need a fair amount of nitrogen. Root crops, and then those that are also legumes like peas, do not need as much. So when we look at soil tests, they're great to have, but remember they're just a point in time. So things like nitrogen are going to fluctuate every year. Depending on what kind of fertilizer you added the previous year, that will also change things. And then also whether or not you grew any crops in there. So if you had a garden, didn't grow crops the previous year, and then you went back and tested it 2 years later, it's going to be much different than if you measured it 2 or 3 years ago. If you're really worried about your soil nutrients and how they're getting to the plants, you could take another step up and actually measure plant tissue. Then you would know actually what nutrients are making it into the plant. And typically we will do this to rule out disease and other factors when plants do not seem to be responding to fertilizer. The other thing that you can do in terms of trying to figure out what's wrong with your plants and if you need fertilizer is to watch them. There's different indicators with plants to determine if they're starting to get low in potassium, if they're starting to get low in nitrogen, and we can watch for those signs and determine what to do next. So how do we determine on our own to figure out how much fertilizer we need to add? There are ways to do this, and let's talk about that. So right now what I'm going to do, and hopefully I won't break the internet, I'm going to switch over and show you guys my website and the soil calculator I developed. And this will allow you to basically get your soil report and then enter in all your own information, and it will calculate everything for you. And when we do that, you're going to be able to interpret everything as you go. So let's do that. I'm going to create a new share, and we're going to switch to the internet. And so now you guys should be able to see my internet. And the easiest way to go to our webpage in the Kenai district is just to type in Kenai extension. This is the only place that the calculators are housed. So now we're just going to hit enter, and that will take us to the link for the Kenai page. Click it again. It's going to take us to our page here. And now that we're on the page, I'm going to remove the little notification at the top, and we're just going to scroll down to the bottom left. And that gives us our options for soil test interpretation. Now that we're here, you just choose the right soil test that reflects what you did. So if you have a garden or farm soil test, you choose this calculator. If you have peonies, you would choose this calculator. And if you have trees and shrubs, you would choose this calculator. So we're going to assume that we have a regular just garden at home. We're going to click on this link, and it will take us to another page. And in just a second here, it will populate a spreadsheet. And with this spreadsheet, we'll be able to go in and enter in all the numbers we need to figure out what we need to add to our soil. So I just wanted to quickly show you guys that. We're going to switch back to the other presentation now, and then we will come back to this in a minute so that I can enter some numbers so you can see how this works for you. Okay, so now we should be back on the presentation. Again, I'm just showing you here. This is that chart that comes up with the different links when you go to my page. Also on here is just another picture of what it looks like when you're there. And then here is the output area that you'll see once you enter in all the numbers. It gives you organic options above, you have different ones you can choose from. And then below it has conventional ones that you can choose from. And on the left side, once we enter in numbers, it will give you a percent match and will tell you which is probably the best fertilizer ratio that you should choose to add to your soil. So that's what it will do. And then at the bottom of that, once you've scrolled down through all of it, it will give you the relative interpretation numbers to be able to use alongside what it spits out. And so when it tells you it's low or moderate or optimum, you know what those mean. Okay, so before we go on and enter in all that information, let's talk about some of those different types of fertilizers that are available. The number one fertilizer that's used to change things around here is lime. Lime raises your soil pH, and so it's available in two main types, powder or prilled. Powder we typically use when it's not windy, when we're not expecting a lot of high temperatures and wind, and it's also used on a large scale, and it also reacts quicker once it rains or you irrigate. It moves through the soil easier because it's in small form. The prilled, however, though, is easy to spread by hand or one of the little whirlybird spreaders that you might use in your garden. And so it's very easy to apply. So the powder is a little harder to work with, but it reacts quicker and changes your soil pH quicker. The prilled is a little easier to work with, and it's easier to get into your soil. Just takes a little longer for it to have an effect. Other fertilizers that you can use is just regular old conventional fertilizer that has nitrogen, phosphorus, and potassium. Some of the ones that you can find are things like 16, 16, 16, 8, 32, 16, 10, 10, 10, 5, 5, 5, 20, 20, 20. There are several different ones out there. This just happens to be one of the common ones that you see. Another organic fertilizer that you might be able to use is blood meal. It has about 12% nitrogen. This is very commonly used. Fish bone meal is about 7% phosphorus. It also has a little bit of nitrogen in it, but the main thing we go for with fish bone meal is the phosphorus. Wood ash has about 8% potassium. We do want to use this very sparingly because it does contain sodium. A lot of folks would like to use wood ash to change their soil pH, but in the amounts that you actually need to apply to change your soil pH, it's actually adding a lot of that sodium to your soil. We don't want to do that. So you either use wood ash very, very sparingly or not at all. And if you've used it once, try not to ever use it again because that sodium really does not go away anytime soon. Langbeinite, another common name is sulfomag or K-mag, has magnesium, potassium, and sulfur. It's a very good source of these items, and it's considered organic. Epsom salt has about 10% magnesium and 13% sulfur. It works great, and it is considered organic. A lot of times when our soil are deficient in magnesium, Epsom salt is one of the first things people choose to go to. Boron. Boron has 11% boron in it, so this borax, I should say, has 11% boron. When you apply it to your soil, it's usually in very small amounts because it's a micronutrient. So the recommendation is usually 1 to 2 tablespoons diluted with 1 gallon of warm water and applied to about a 100 square foot area. And you trickle that on. You can use a watering can or you can use a sprayer, and it's applied to only soil, not to plant leaves. Organic matter. You can apply peat to your soil to raise the organic matter. You can apply manure to raise both the organic matter and nitrogen phosphorus levels. It really depends on what you need, and depending on your soil report, it really influences how much organic matter you should add. So going over here to the left where it says soil testing interpretation, if you go down to the fourth, or actually it's the fifth link down, it's the factors to consider in selecting a soil testing laboratory. This one right here will take you to the page that has the publication on the different labs and things to consider when sending it to a lab. If you went to the next link down, it says request a custom soil test interpretation. When you get your soil test back, what you can do is click on this link and send me your soil test, and I actually will interpret it for you. I put together a 2 to 5 minute video interpreting your soil test for you, and then that helps you figure out how much fertilizer you need to add. So those where those other links are. Let's go on back to that calculator I was mentioning earlier. So with this calculator, we're just going to go ahead and enter some numbers. And since I have done probably close to 2,000 soil samples now, interpreting for folks here in Alaska, I'm just going to add some numbers that are about what people might encounter. 5 for cation exchange capacity. I'm going to put in 6.3 for buffer pH. Regular pH, I will put it at 6. Organic matter, I will put down at 11. Not going to worry about the nitrogen release because, again, that really doesn't matter for Alaska too much. Sulfur, I'll put in at 9. Phosphorus, 33. Calcium, typically it's fairly high here in Alaska. Magnesium, we're going to go down to 66. Potassium, 82. These are all common areas for numbers that I typically see. For sodium, we're going to go ahead and put 102. And then from a soil report, you'll typically get back a number. The little bit more expensive ones will have the base saturation number, so I'll put that in here for you. Let's go ahead and put it in at 5. And usually you'd want to make sure these all add up to 100 on your soil report. And I will just put this in at 34 because I did not do the math. And then we're going to go down here to boron. Typically people will have about 0.5. Zinc. Put 0.65 for soluble salts. Chlorine is typically not given on a soil sample unless you ask for it. And then nitrate, nitrogen, we're going to go ahead and put at 12. And the ammonium, I'm going to put at 11. And then once you've entered all of those, it actually calculates everything on the right-hand side. Scrolling up, when you look at this, these are the amounts that you'd want to apply. So based on our soil, because it's not an organic soil, and we have a buffer pH number, it tells us exactly how much lime to add to raise the soil to 6.5 pH. So here we would need to add 13.2 pounds of lime per 100 square feet if we want to get to 6.5. If we were trying to actually get to 6.5 to 7 pH, we'd want to add 15.8 pounds per 100 square feet. Going on down and looking at sulfur, it's asking for 0.06 pounds of sulfur per 100 square feet. This is just sulfur nutrient. It's not the actual type of fertilizer amendment. This is just the amount of these different types of nutrients. So you can see we need a fair bit of phosphorus, a little bit of magnesium, and a fair bit of potassium. We're going to need some boron in the form of borax, and then also we're going to need some nitrogen. Okay, so what does this mean in terms of amendments? Going down here, looking at your organic options, you could choose blood meal to meet your nitrogen needs, and here it would be 2.9 pounds per 100 square feet. You could use bone meal to meet your phosphorus needs, and that would be at a rate of 2.5 pounds per 100 square feet. And then for potassium, you've actually got a number of choices. You could use wood ash, you could use langbeinite, which is also that sulpomag or K-mag. You could use potassium sulfate, or you could use potassium chloride, which is muriate of potash. You could use any of these here for your choices, but the thing I look for is that these things also have other nutrients in them. The langbeinite also has sulfur and magnesium in it. So I see down here I also need sulfur and I also need magnesium. So I'm going to go ahead and use langbeinite at a rate of 1.3 pounds per 100 square feet. And that's actually going to meet all of my needs for it. It's going to add me a little bit more than we need for sulfur, that's going to meet all the needs for potassium, magnesium, and sulfur. So typically, langbeinite is one of the top options. The next option would be potassium sulfate. And for magnesium, the two main options usually are either langbeinite or Epsom salts. And so if we didn't use langbeinite, we would still probably want to add in some sulfur if we use this muriate of potash, because it has no sulfur in it. And because we need magnesium, we would just use Epsom salts that are rated 1.1 pounds per 100 square feet. So that's what you want to be looking at here in terms of those amendments. Those are the organic options. And then, of course, the borax, whether you do conventional fertilizer or organic, borax is considered an organic fertilizer. And that would be 1 tablespoon diluted with 1 gallon of warm water. And once that's diluted, you would apply that to each 100 square feet of your soil. And that would approximately raise your boron level by about 1 part per million. If you chose none of these organic options and you wanted to use a conventional fertilizer, you would just go over here and look at your percent match. Looking at this, we can see that actually an equal ratio of nitrogen, phosphorus, and potassium is going to be our best choice at nearly 99%. So I like to go with those that are high in nutrients, like a 20-20-20 or 16-16-16, because for every pound of fertilizer you're getting, this right here would be 60% fertilizer, because that 20-20-20 are each percentages. So I don't want to pay for a 5-5-5 because that's only 15% fertilizer per pound. I'd rather buy the fertilizer at the same price at 20-20-20. So using that fertilizer, I would need 1.7 pounds of fertilizer per 100 square feet. And that's all I would need.